Anybody have the answer to the homework question? All right. I guess that's a no. All right, let's move on. Now, the syllabus requires for us, right, to identify origins, right, of background radiation, right, and also look at, the implication, that these background radiation can have on us. What you have to understand right now, as we very much speak, there's a lot of radiation in the atmosphere. We as a science students need to know what is causing those radiation, right? And how, I would say, maybe we can try to limit some of that from entering our body, right? But for the most part, we'll look at it. So it says to us that we are continuously exposed, right, to natural occurring radiation from outer space as well as from rocks, the air, building materials, our food, and trace elements in our bodies, in our own bodies. So a lot of radiation is about the place, guys, right? So sometimes you have to really wonder why some persons end up getting cancers and all of those things because, things can happen, right? Now it says that radiation coming from out of space is what we call cosmic rays, right? So that's what we call cosmic rays. And it says that cosmic rays, which are mainly energy protons, right, or to a lesser extent, nuclei of atoms other than hydrogen, right, that have been stripped of their elements, account for 16% of our natural or annual natural radiation dose. Okay, so that's why it's kind of good to see inside sometimes. So all for those who want to run up and down right now and all of that, praying for the pandemic to be over with and all that, you're actually helping your own self to some degree, right? Less exposure to cosmic rays, right? So that's one source of radiation, and we can see that it contributes to 16% of our annual dose of radiation. Good. There are other sources, and we're going to look at those in short order. Right?
Sir, can go back, please?
There you go. So if your syllabus asks you to identify the origin of some background radiation, this is one example. It says cosmic rays, and that is the one that comes from outer space, right? And it explains to you what a cosmic ray is. It's just some energized protons, or for the most part, some type of nuclei that are traveling towards, the Earth, right? Are you finished now?
No.
Okay, good. Yeah. So the next origin of background radiation that we're going to talk about is what we call radon, right? You probably have heard about radon for some chemistry persons. Anybody have ever heard
Sorry,
about?
I can't hear.
All right, thanks. Anybody ever heard about radon before? Well, I guess you haven't. But radon is pretty much a, one of the data elements or the data nuclei from when uranium has been disintegrated. So let's see what it is saying here. So radon is obviously it's a gas that is produced by natural decay of element uranium present in rocks. So generally uranium is found in rocks, right? And it says that this radon gas is generally found in soil and has the potential to get inside of buildings from underground water sources. So this is now another origin of a background radiation, right? And it says that this gas is the biggest contributor to our natural radiation dosage or exposure, rather, right? And it says that this gas cannot be seen, it cannot be tasted, it cannot be smelled, right? It says radon gas can contribute to lung cancer. So you might hear a person who have never smoked before and they end up with lung cancer. And you wonder why they end up with lung cancer, what could be the cause of that? Some of these things could literally cause it. You see what I'm saying? So we have to be mindful, and for persons who are going into the manufacturing industry and going into the construction field of engineering and so forth, it's of paramount importance that you take into account these things, right? To see how you as a developer building houses and all type of buildings can reduce this, because the radon can seep into the water. And when you seep into the water now, let's imagine that you're looking at the diagram. For argument's sake, let's imagine that the water that you use come from a well, right? And radon was seeped into it. And that water is now running to your home and to your pipe, and you are showering using that water, or you are actually drinking the water, right? The gas, because we know gas is dissolvable in water, so it can actually travel in the water, right? And for that reason, it can end up in your house eventually, and of course affect you at the end of the day, because it's a type of radiation. So and we know about radiation, it gives off a lot of energy, right, when it disintegrates. And not only that, it's going to break down further into other nuclei and so forth. So this is the biggest contributor. We know the source, so naturally it is found when uranium goes through its process of decay, right? And we're saying that it is found in the ground. So like persons who like to play in the dirt, maybe you're taking up some amount of uranium. Right? But yeah, it's a very dangerous gas though. But what I can say, I think technology has become the better of us. So we can actually design detectors, right? I was back in the days, I normally look at projects where you could actually create detectors that could sense the different types of gases in the atmosphere and so forth. So in modern buildings, right, some of the times when you see those things flashing, sometimes those are just to detect the type of gases in the atmosphere, right? You can test the carbon monoxide level, that kind of thing. So technology is here so that we could use that in itself to pretty much limit, or just to check on a whole to see if radon is in the building and all that. And this has killed a lot of persons, by the way, right? Right. And when I was doing the research, it has killed a lot of persons in UK and all of that. So we need to be mindful. Now, as it pertains to food, now you actually have some type of radiation in your food, right? So this is another source of background radiation. It says that our food contains small amount of natural radioactive materials. For example, many food contains tiny amount of radioactive potassium 40 or lead 210 or polonium 210. I think there's an error right here, maybe, right? Then it says that these radioactive substance, right, becomes concentrated in fish and other animals and are passed to us when we eat these animals as food, right? So while we might not take it in directly, but certain animals eating certain things, right, could essentially have those elements inside of them, and of course we can end up, you know, um, getting these things in our body. You understand? So yeah, that's really what it is. So that's another source as well. So we have identified at least three sources and the origin and how it can have an impact on us, or hazard to the environment. Are we good? All right, I believe we are. All right, no is
Sounds correct.
that's what I asked you, but you never answered me yet. So that's the reason I changed it. So I pretty hope that when you're studying, you take the PowerPoints that I give you and you parallel it with the syllabus to see if information is in it pertaining to what the syllabus requires for us. And even sometimes the syllabus does not give us all information.
Sorry, I can't change.
All right, thanks. Background radiation now, right? We have to consider this thing about background radiation. What if I am measuring a source of radiation for argument's sake, right? Now I have to take into account that there is a possibility that background radiation is in the atmosphere. And for that reason, if I'm counting the amount of radiation using some type of device, we're going to look at those eventually. I have to make a calculation because that background radiation will ultimately add to the or it can give you a wrong reading if you don't consider it. You understand? So this is what we have to do. We have to literally, get what we call the corrected count. And how we find the corrected count is by way of just subtracting the background radiation from the total count rate, right? So whenever we are trying to count radiation, you'll hear us talking about the count rate, which just speaks to the amount of radiation that is passing through this at a given time or all of that, right? So if I can identify the count rate, the total count rate, and obviously measure the background radiation by itself, then to find the corrected count rate of the material, you would subtract these two things. So let me just highlight this again. So what you would do, let's imagine that you have a radioactive source, such as uranium, right? And you want to measure the count rate, which just simply speaking about the radiation that is being given off, right? You would have to, before you start measuring the count rate of the uranium, you would have to measure the background count or the background radiation in the environment that you're doing it. So if you're doing the experiment in a lab, you have to use your galvanometer, which we'll soon talk about that, right, to measure the background radiation. So when you get that value, you say, all right, this is the amount of radiation in the atmosphere. So when I do measure my count rate, right, my total count rate, that is going to be the count rate of the source plus the background radiation. So I have to do a corrected count, which is to subtract the background count from the total count rate. You see it? You get the message now? Yes or no? What I'm doing? I understand. When you open an alright, why not? radiation, like on down on this, and we're not hearing from us, right? I guess I can move on, next my slide because I'm not hearing anybody saying anything here, right? Okay, wonderful. All right, yeah. So pretty much these are the sources, right, that we have talked about in terms of the background radiation. We said radon gases, right? We didn't make mention of the artificial sources of background radiation, but I must tell you, I think there is a country. I was watching a documentary one time. There's this country where the U.S. would have been, it's a small island, where they were doing a lot of testing as it pertains to nuclear weapons and so on. And I mean, man, the soldiers that were involved in all of that. I mean, they got so much damage from the radiation and so forth. And one of the ways how these these countries try to get rid of these waste, these radiation waste, is by digging like a big well, or not a well, but a big pit in a sense, and pretty much bury the fragments of the the nuclear weapons and so on. So to kind of like prevent that from escaping in the environment. But as you can imagine, some of it is going to seep into the environment somewhere or the other. It might seep into the underground water and all of those things. So that's also another source of background radiation by way of nuclear weapon and all of that, right? So that's pretty much what we need to make mention of in terms of the background radiation. I think the next slide should be talking about, yeah, the biological effect of nuclear
Sir, can you
radiation.
go back a second, please?
Yeah, yeah, man. The next thing we're going to talk about is,
You can explain the, huh?
say that again?
Can you explain the one with the rocks?
The rock?
Can you explain the one with the rocks?
Okay, okay.
Yes.
Yeah, so you see, I think like uranium, right? Uranium is found inside of the rocks, right? So there are certain elements that very heavy elements, they are actually found inside of the earth. Remember that most elements are can be found in earth for the most part, and uranium is one of them, right? So that's what it means here when it says that rocks contain naturally occurring radioactive isotopes. So uranium will disintegrate into radium um, gas, and that radium gas can eventually seep into our waterway and all of that. Cool. Yeah. So that's that. Think you're finished now? So,
Yes, sir. I was Googling something.
all right, good, good. Biological effects of nuclear radiation. So there are huge amount of there are benefits with radiation, right? And there are also the harmful aspect, you know what I mean, of radiation, right? We know that radiation gives off energy, right? And if we're not mindful, those energy that it gives off can actually damage our biological cells, right? But also in certain treatment regions, you're going to look at that eventually. You're going to look at that soon. But these are some ways in which the radiation can actually affect humans, right? When some persons are going through cancer treatment and so forth, they can actually, become burnt by the radiation. You understand? And it ends up leading to what we call acute radiation sickness, right? So long exposure to radiation can make you, I don't know what the sickness is described as, but um, I'm thinking it could be the burns that you're receiving from it, right? But you can also damage your genetic um, DNA, or your genetic information, such as your DNA. So that's kind of like one of the reasons why, they recommend that we should not you put the cell phone, like if you're driving, you should not have the cell phone between your legs and so forth, because there's some type of radiation being given off from the cell towers and all of those kind of things going towards the phone and all of that, right? Um, and what else now? You know,
Excuse me, sir.
yes, go ahead.
Like, what is the exact reason why females can't do radiographs when they're pregnant? Like, what exactly happened to the fetus? Or is it a case where they just, trying to not, I don't know. What exactly happens?
Yeah, as you can imagine, right? They remember the baby
It
hasn't
said
been.
something about genetics or something like that. I don't
Yeah.
remember.
So let's look at it,
Or DNA. Yeah.
right? It can remember the baby hasn't been developed. You understand? So the cells are really fresh and not even strong to can even function on their own. So you don't want certain amount of energy from the radiation to be passing through the parent. That is kind of like one of the reasons why they use ultrasound when they are doing the testing and all of that, because that is more of a safe method of getting their checks and balances with the baby and so on, right? So it's really related to that, because I mean, you don't want to run the risk, you understand, of passing X amount of energy through the baby, which the brain probably is not even fully developed as yet, and all of those kind of things, right? We know that radiation can cause damage to cells, and we don't want to run the risk of putting the child into that harm's way, right? So as you can see here as well, I mean, this whole radiation thing can ultimately lead to cancer, because if the cells are damaged, remember now, tumors are developed based on the fact that cells are growing irregularly, and if the radiation is causing the damage, then those cells are going to grow irregularly, develop into tumors, and ultimately then develop into cancer, right? Um, yes, see, we're saying that it can cause birth defects. So imagine that you were exposed to radiation long term, that can damage you know the cells for your reproductive system and all of that, right? And eventually would can lead to some type of birth defect and all that. So persons that are working in the radiographic department, they have to have what we call, I don't remember the name of it, but there's a small thing that they walk around with, right? That is always on their body, right? In a specific location. It's a photographic something. Let me see if I can see the name. Give me a second. Um, I know I have it here, but I don't remember the name of it. It's a photographic film, right? While it doesn't look mainly like that, but it is what they use. They walk around with it, and each about maybe every 6 months or so, they have to go and send it off to testing to see if any excess amount of background radiation is being given off in the department, right? So when they do test that, they can see if, depending on what is happening on the film, right, then that will determine to say, all right, this amount of radiation is being, X amount of your body is being exposed to radiation. What if the entire film is black? You understand? Then that could say that, all of your body is being exposed to radiation. What if one side of it is black? Then it means that only a half of the body is being exposed to radiation and all of that kind of thing. So, there are things put in place, but, it's still really not safe to see me. So that's why they allow us or allow those persons to wear particular gowns that can pretty much block off some of the radiation. So I'm saying, or they tell you to stand X feet away or behind some type of window, because they know that radiation in the background can actually harm them, right?
Excuse me, sir. He said maybe that's the reason why pregnant women do ultrasounds to check up on the fetus, or if they're checking for anything inside their body, like you know organs,
Mm-hmm.
to check if something's wrong. All right, you said that's much safer, right?
Mm-hmm.
But why is it that you can't do it like like 3 times a year. Is it that much?
Yeah, man, of course, man. We are talking about it's a lot of radiation, man. We are talking about it's a lot of radiation that passes through the body just by you going to do a regular scan or something like that. You know what I'm saying? You follow me?
Yes, sir.
Yeah. Yeah, man. Everybody know, you know. I mean, we don't really want any child that has any birth defect. I mean, that is going to be a hard thing for you to deal with at the end of the day. So try to just prevent that.
No, not the child,
But
as
what?
in you yourself, your body.
So you're saying the question you're asking is that if you need to do a radiation, like to take a scan of your body, that's what you mean? And you're pregnant or what?
No, let us say you have to do an ultrasound
Okay, yes.
somewhere on your body.
Uh-huh.
Why is it that you can't? I was asking if it is because there's so much radiation taking place that you can't do it like 3 times per year, or it's not recommended, or they won't that you do it a second time if
Mm.
the time is not foregone.
Yeah. It's really because of the amount of radiation that essentially has to be used on the body. You understand? Just to get that one image that they want. You know what I'm saying? Because I mean, sometimes they actually have to inject even some type of radioactive element inside of you, and that while it have a very short high half life, that we'll soon talk about it, right? I mean, what if you're doing that so often, ever so often? It can have significant implication on the body. So it wouldn't be recommended to be having those scans often because it can lead to damage because as we can see it can cause cancer. You understand? And they know that for a fact. While it's good to see what's happening inside of the body, but you know, and everything where is good is gold. So pretty much. All right. Now radioactive isotopes, right? Let me see the time here. All right, good. So wow, these are you know, as we know, isotopes are different forms of the same element, right? Which just have maybe an extra number of neutrons to just increase the overall mass of the element, right? So that's what we call isotopes. So if we're dealing with radioactive isotopes, these are just pretty much elements that are of the same element, such as maybe like a hydrogen. We know that hydrogen has different isotopes, right? And possibly one of those isotopes can be a radioactive substance. So a typical radioactive isotope is something that will disintegrate over time. You understand? So there are various applications of it though, right? As you can see on the screen here, a thing such as cobalt 60, right? It is used in the prevention of or it's used in radiation therapy, right? Um, there's so many of them. Carbon 14, right, is used to study metabolism changes for patients with diabetes and so forth. So you see, a thing like carbon 14, I think that might be a thing that you ingest because you have some stuff that they ask you to ingest, right? And that could the way how this works though is that you would ingest it, right? And they would use a detector to detect the radiation that is coming from it, right? So when that radiation is detected, it can paint the image that they want to see, right? And not only that, this element carbon 14, right? Based on studies, it would have shown that that carbon would more than likely drawn to that area of the body. So let's imagine that you want to look at the what you call this now, like the pancreas and all of that. Possibly that carbon 14 likes to attract itself around that region, and so it could give off certain radiation in the process, and you can pick it up on a detector and all of that, right? So there are several uses of it. If you look at it, sodium 14, that is used in the study of blood circulation. So you would find that element. So when you put that into the blood now, right? We generally call those, I think we call them tracers. So you inject that into the blood. It goes around in the body, right? And it has its own half-life. See, as you can see, the half-life is 15 hours. So, having that passing through the body now, right? You can detect the radiation when it is being given off based on the fact that its half-life is 15 hours. You understand? So that person who is doing that study could take that overnight and come back to the place on time to get the scan done and all of those kind of crazy things, right? The most important one though is titanium, right? 99. That one is one that we generally use, and we have to kind of be able to kind of explain how that one works in the medical industry and so forth, right? As you can see here, it locates brain tumor and damage heart tissues or heart cells, right? It's a radioactive tracer that is used in medical diagnosis. So it's a widely used, radioactive isotope. Cool. And as you can see, the half-life here is 6.0 hours. So it have a much shorter half-life. So it is more safer because it will disintegrate much faster out of the body. You see what I'm saying? So that is kind of like one of the reasons why you would use such a thing, because of the fact that it has a much shorter half-life, right? You don't want the radiation to stay in the body for too long, because that can have serious implications. And you have to know the amount that you're putting in as well, the dosage and all of that. Let me see something here. Yeah. All right, the reason why I made mention of this right here, obviously carbon-14 is a radioactive isotope, right? And there's a process of what we call carbon dating. And carbon dating has helped us a whole lot when it comes down to identifying certain historical facts and all of that, and to see how long certain things have been in existence for. I mean, it's a very interesting thing, right, to see how they do it. But what we have come to understand is that every living thing has a set amount of carbon-14 inside of their body, right? And when they die, that carbon-14 will essentially start to disintegrate, right? And it has a half-life. By the way, we must remember at least carbon-14 half-life. That is 5,730 years, right? So we must remember at least that for in terms of the half-life, good? Or even for titanium, right? Which is practically 6 hours. Some of those details we have to remember them. So we're saying here, because they know the approximate amount that, a living organism would have, they can now predict based on the amount of carbon that is remained in the dead organism, right? And determine how long it has been there for. You understand what I say? Right? Obviously, they could not have waited until 5,730 years to find the first half-life, but they know how to do it. You understand? Right? To literally find that percentage of carbon that is remained, carbon-14 that's remained, and see how long it has been present for. In your free time, you can watch this video. I did post a video here that you can watch as it pertains to carbon dating. When it comes down to the Bible and all of that, right? It's really carbon dating that they would have used to get some of these dates correct. You know what I mean? About the years long when Jesus was on earth and all of those kind of madness and the whole dinosaur and all them something, right? So, yeah.
Oh, sir.
Yeah, go ahead.
As you talk about age, I just Googled something and it was saying that you can use like a bone sample to do a radiograph on it.
Mm-hmm.
They normally use like the wrist and the femur to approximate the age or something like that.
Yes, that is true. I came across that sometime as well. I wanna. All right. Yeah. The person was saying something a while ago about the risk. Yeah, I came across that um at some point. I don't remember when I read it, but I read something related to that. Is she back on?
Yes, sir, I'm here.
So I'm wondering what did they say exactly was in the risk that caused them to can easily it's the growth rate of the bone, like that bone, right? There's something about the growth rate of it. Let me know. Tell me if what else you got from that information. If you got anything else.
Sir, some this type of plate, some epiphyseal plates or something like something about the bone.
Mm.
Yeah, something like that. I don't remember.
I urge you guys to go and research and read up on that a little bit because these things are very interesting. I can say that, right? So read up about it a little bit just to just gain a little bit more knowledge. I don't think nothing is wrong with knowledge, So you can do that, right? I'm gonna do it myself as well to see what exactly is going on there. But I think it might have to do with the fact that that bone, it grows continuously with the body. I guess I'm trying to think maybe, right? But I'm gonna read it up and see what happens.
Yeah, because they were saying like if you X-ray a child's hand
Uh huh.
and an adult, you see that the bone is different and like it grows according to age range. Like some
Oh
bones are
yes,
yes.
yes, yes. You're right. Yeah, yeah, yeah. I'm gonna go back and read up that again. But I did hear about it. I did hear about it. Good information, right? So yeah. So there are actual applications that we can see as it pertains to radioactive isotopes, right? We saw where titanium, which is the more commonly used one, it is used in a lot of the medical industry, right? Where we can see, it's going to be used to basically aid in the whole diagnostic tools to basically identify cancers, those kind of things. It can also be used in the whole um, treatment process of certain diseases, right, to damage those tumor cells and all those kind of madness, right? So titanium now, right? It says here that is and as a matter of fact, the syllabus requires for us to know the characteristic of this, why it is generally used in the medical fraternity, right? And the answer is right there. It is because of the short half-life. So let's look at it. And not only that, it emits relatively low gamma rays. So let's see what it has to say. It is the most widely used nuclei for diagnostics, right? Um, and it has a short life, which is 6 hours basically, and it emits relatively low energy gamma rays. It can be injected into the body as part of various chemical compounds designed to concentrate in specific organs or potential tumors. So, for example, in the lungs or the brain. So what you see here is that based on how titanium works. When it is injected into the body, it can find its way, right, to specific organs. Yo, you may say right now, I like pronounce words, right? Tectesium. Thank you. Right? Yo, thanks, Ennis. Thank you for that. Right? Tectesium, if that's how it's pronounced, right? Um, yeah. So, so yeah, man. So it can find its way into certain parts of the body. You understand? And can target the tumors, the potential tumors that are there. You know what I mean? And could literally use the energy that it is giving off to literally damage it, right? But not only that, the gamma rays, right, emitted from the tectesium, right, are detected outside of the body with um, a gamma ray camera, right, which produce an image of the area under investigation. See? So while it can be used to pretty much destroy the tumors, right? It can the radiation that it gives off can then be used to um, see what is happening inside of the body, right? In those specific areas. Okay. All right. Let's see what time
Sir,
it
I'm
is.
writing.
All right. Good. Good. Yeah. So note the mass number for tectesium, right? Note that, and you see the characteristics right there. So that characteristic is important. So may I say, the half life, the short half life, and the fact that it emits relatively low um energy gamma rays. Now we're almost on the wire. We're almost wrapping up. So chances are by about next week we can be finished with module 3, and we can then start our revision process, right? Going back over some stuff that someone understand and all of those things, right? But you guys have your own part to play. You understand me? I say, right? You know, some of you would have missed a
Sir,
few.
you can change.
All right, good, good. Yeah. So we have been talking about radiation, and what we must make mention of is the fact that there are different types of radiation that can be emitted from a source, right? You would have learned about these already, right? In let's say fifth form thereabout, right? When you were learning about radiation, right? You know that there's alpha particles that is pretty much a type of ionizing radiation. You know of beta um, particles that is being given off. That's what we call the radiation, of course. And you have gamma rays, which is not necessarily a particle, right? But is more of a electromagnetic, light or electromagnetic radiation mainly, right? And we know that these particles can travel to certain ranges, right? And what we're going to look at here is to see what can stop a alpha particle, what can stop a beta particle, what can stop uh, a gamma ray. You understand? Right? Gamma ray is really hard to stop. As you can see, it's like light traveling. So, lead obviously is the one that can stop it. So a few inches of lead could stop it, or depending on how thick a concrete surface is, that can actually stop a gamma ray. Right? We know already that a thin sheet of paper can stop alpha from from um, from being emitted, right? Or from passing through something. Yeah. But let's try to understand what ionizing um, radiation is, right? So how does ionizing radiation occurs? So let's imagine that we have an element, right? And there is some, yeah. So yeah, when certain elements undergo radioactive decay, right? It obviously causes radiation to be given off, and it can either be alpha particle, um, gamma, or beta. Now, as it pertains to ionizing radiation, the reason why we call it ionizing radiation is because of the fact that those radiations are able to knock electrons out of certain shells of different elements, and or different not elements, but yeah, just knock electrons from the shell of an element and all that, right? That's kind of like the reason why we call it ionizing radiation, because it actually has the ability to knock um, electrons out of a shell, right? It has enough energy to do that, you know. Let's see here. It says that when radiation passes through matter, it causes electrons to be knocked out of the atoms. This results in the formation of ions, right? For example, a beta particle moving through the air will have enough energy to knock electrons out of the air molecules and leaving a trail on, I think, of ions behind it. It says as it ionizes the air, it loses some energy and slows down. So yeah, as that beta particle or the alpha particle, knocks an electron from an air molecule, you expect it to lose energy because some of the energy is going to be converted, or going to be used to set off that electron to pretty much, um, move to some other location, right? So that's kind of like the reason why we call it ionizing radiation, because it's performing that process of,
Sir, can go back, please.
yeah. There's one very important part that I will have to go, and I know it's not in this, but it's using magnetic field to pretty much identify the different types of ionizing radiation. That is something that you must know if I don't even go through it, right?
Sir, can you?
You must know that part to see how these different radiation behave in a magnetic field, right? And I think you guys would have seen it in fifth form, right? Yes or no?
See what?
There's a particular way how we can use magnetic field to detect alpha particle, beta particle, and gamma, right? This is our magnetic field. Right? Because the fact that alpha particle is a positively charged hydrogen, not helium, right? But helium. Because it's a positively charged helium, right? You would expect, if this is a magnetic field, I think this is the X symbolized is going into, right? The X symbolized going into, is that correct? Into the paper. So this is what is happening here. If I don't get a chance to speak about it again, I must speak about it now. So we know alpha is positively charged. So here's our alpha particle, and it's going towards the magnetic field, right? We would have to obviously use the Fleming's left-hand rule here to predict the direction that the positive alpha particle is going to move. So, FBI, in a sense, FBI, that's how our fingers have to be positioned. So your thumb is force, B is the magnetic field. In this case, we're not going to use I, we're going to use, let's use F is equal to BQV for this. It's better if we use this. This one is involving current, and we don't want that. So alpha particle is positively charged, right? it's moving towards this direction. So it therefore means that it's going to go up into the air like that. If you were supposed to position your hand using the Fleming's left-hand rule, this X means going into the paper. So your first finger must be pointing into the paper. Then your second finger is pointing towards it's our right. Yeah, that's the right. And obviously your thumb now is going to point up into the air. So generally speaking, if I wanted to detect whether this is alpha or beta, if I see that it is going up into the air, then I must know that providing that the magnetic field is going into the paper, this is going to be an alpha particle. As it relates to a beta particle is a negatively charged particle, which is an electron. So because it is negative, right, we have to treat it opposite to how we treat the positive. So because the positive is going in this direction, we're now considering that the negative is going into the opposite direction. So what I would have to do is to identify my magnetic field, rotate my hand so that my second finger points in this direction. And then what I would see is that the beta particle would be going like this, right? That's how the beta particle will be going. Good? Essentially going down and eventually turning out of this magnetic field, because you know particles generally move in a helical path, in a circular motion pattern, right? And for the gamma now, gamma is not deflected by a magnetic field. So you would expect that the gamma, oh, you write this again, so you write it, yeah. It would pass through undeviated. So this is talking about the deflection. In your reading, you'll see it, deflection of ionizing particles using a magnetic field. I think it rings a bell a little bit. No, I'm not sure, but let me know if you have seen this anywhere in your physics career so far. Yes or no?
I don't remember.
Oh, you don't remember? All right, we're gonna look
I
at
don't
it.
know.
Yeah, man, but it's something where me know for a fact that it was supposed to be taught. So we're looking at deflection of ionizing radiation using magnetic field, right? So let's look here. Let me see if I can find, right? So this is what essentially we're talking about, right? So you can see the alpha particle right here. It's going up like this, right? And as you can see, they're using the Fleming's left-hand rule. Good. They're saying that X, which is the magnetic field, is going into the paper. Beta particle, because it is positive, it's negatively charged, it's going to slow down like this, right? They say that beta is negatively charged, alpha is positively charged, so that's the reason why it moves up like that. So in order to get this correct, you have to use the whole aspect of Fleming's left-hand rule. There's another scenario though that they can even show you as well, and it's related to this, using charged plates, right? So let's imagine that you have a charged plate. Good. One section is positive, one section is negative. Obviously, because alpha particle is positively charged, it's going to move towards the negative plate in a parabolic motion. Gamma has no charge, so it's going to pass through undeviated or undeflected. And beta, being negatively charged, is going to obviously move towards the positive plate. All right. So that's just really it. This one here, I believe this speaks to the fact that the magnetic field is going out of the paper, right? So that's the reason why it's like this. Well, not necessarily. They didn't state. If we were to rotate this, right, it would have been the same thing that we have been discussing so far. So I'm assuming that the dots here are not being used to represent the magnetic field in and out, right? Yeah. So this is like what I'm talking about. It's a much better diagram. So sometimes they can ask you to draw this, you understand, to show how the particles deflect in the magnetic field. And they can even, so you see how they can tie things together now. They can tie magnetism into the whole concept of of radioactive decay, or in module 3 per se, because they can go ahead and say, all right, determine this and that, in terms of the magnetic field, determine the speed of the alpha particle, that kind of madness, So it happens from time to time, and we can't neglect anything that we know. Okay. All right, we have some more stuff to talk about, and we're not going to finish today, right? Obviously. But you see, all things like these, we must know the things that can stop these type of radiation. And as you can see, this part here that says deflected. So I must point out something. Let me go back a little here, right? The thing that I showed you just now, I showed you two things. I showed you the magnetic field deflection, and I also show you the electric field deflection. That the electric field deflection was when you have the parallel plates, positive and negatively charged, right? We see that the radiations were deflected to and from the plates for the most part. So there are two ways that they can actually detect it, or to show that an alpha particle is present or so forth, right? By using both the electric field and the magnetic field. Good. As it pertains to the ionization power, let's give me a few more minutes. As it pertains to the ionization power, right, we can see that alpha it has a lot more ionization power because it is more heavier. It's a helium helium, I wouldn't say helium atom, but it's a helium proton in a sense. So it's more heavier when compared to a beta particle, which is simply an electron, right? So an alpha particle would more than likely be able to can knock an electron from the shell of an air molecule and all of that, right? Gamma now, it is very weak in terms of its ionization ability because it does not have any mass to it, so to speak. You understand? Because it doesn't have any mass to it, it's light basically, so it wouldn't necessarily interfere with the particles or the electrons in the shell of an atom and all of that madness, right? So yeah, very fun information, lot of stuff here for you to digest. All right, I think I should be able to can post the PowerPoint now because I had some corrections to make to it and all that. All right, but I think that's where we're going to stop for today, and we're going to pick up.
Sir, can go back, please.
There you go. I must tell you that module 3 is not the hardest module, right? It's what I say. By the way, I heard something. I'm not sure how true it is, right? Not rejoicing per se, but they have it to say that CAPE or CXC on a whole might make some adjustments to their exam papers, or to the exam on a whole because of the coronavirus and the St. Vincent volcanic eruption, right? So yeah, we don't know what can happen yet. We don't know what will take place. So let's see. All right. But that's it though. That's it for today. Hope you guys learned something.
Sir, finish, sir.
All right, yeah, man. That's it though. That's it for today. All right, we'll pick up this next week Monday, and start up the loose ends and to see if we have met our objectives. All right. Blessings.